you can solve a Putnam problem. If you've watched all my calculus videos and have a solid understanding of algebra, you can solve a Putnam problem. And it's also a proof that 22 over 7 is greater than pi. Now, at first sight, this seems obvious. 22 over 7 is like 3.1428, so on, and pi is 3.1415, and so on. And over here, you can clearly see that this is greater than this. But you have no way to prove that without just finding the values of 22 over 7 and pi. So, we are going to solve an integral today. And that one integral is going to first show that 22 over 7 is greater than pi, and perhaps even cooler than that, the fact that we are going to solve a problem from the Putnam exam. Now, this exam is taken by undergraduate students all over the world, and it's a chance to test your mathematical prowess in some of the highest level math in the entire world. And it's so hard that the median score is a 2 out of 120 points. That means you're scoring less than 2% to be average on the exam. You can literally fail according to school standards and be in the top 1% of all competitors. Now, to be fair, this is the 1968 Putnam exam. I thought it would serve as a really good title and thumbnail, and it is like A1, but it's still very interesting just for the fact that it's a Putnam problem, and they thought it was very important enough to be put on that such a prestigious exam. And who doesn't like to know that 22 over 7 is greater than pi? Well, enough garbling, let's move to actually solving this problem. The Putnam exam, the 1968 one, which A1, it says, prove the integral from 0 to 1 of x to the 4th times 1 minus x to the 4th over x squared dx is equal to 22 over 7 minus pi. Now, number one, essentially all this problem asks you is to evaluate this integral, which we will do, and now proving that 22 over 7 is greater than pi takes one small extra step, and that is proving that this integral is positive. Now, how will we prove that this is positive? Well, first, let's draw a coordinate plane. Now we have our x and y axis over here. Now, of course, there's also the negative over here and over here, but we're not going to worry about negative x, but it's essentially the same thing. Now, if I have a function like this, and then this, and then this. Now, this is a very weird function, yes, but the point is not that. The point is this area, which is above the x-axis, contributes positive terms to the integral. But this area, which is underneath the x-axis, produces negative terms to the integral. So, if the integral from this region was positive, we would have to show that this function is positive for all x between 0 and 1. So then you would know that if the y is positive, that means this area over here has to be positive. So let's show that this function is positive. And sorry, it's not x squared, it's 1 plus x squared. Now, so we have 1 plus x squared, and for all real numbers, that's positive. As for all real numbers, x squared is positive. So that's the denominator. Now, over here, I wrote this wrong again. 1 minus x to the power of 4, all of it. And now over here, we have something to the power of 4, which is again just something squared, so that has to be positive, times another positive number since the power of 4 is positive. So we have a positive term divided by a positive term. And that becomes another positive term. So we know that this function is going to be positive for all real x. So it will obviously be positive for a small slice of that real x. So now let's move on to evaluating the integral. So we start by evaluating the numerator. So we have the integral from 0 to 1 of x to the 4th times 1 minus 2x plus x squared divided by 1 plus x squared dx. Now this becomes the integral from 0 to 1 of x to the 4th. Now squaring this gets us x to the 4th. And then after that, if we just do multiplication like this, we get x squared minus 2x plus 1, and then minus 2x plus 4x squared minus 2x cubed. And then after that, we get x squared minus 2x cubed. And then we obviously know over here is x to the 4th. So evaluating all of this gives us 1 minus 4x plus 1. Then we have x squared, and 4x squared, so 6x squared. Then minus 4x cubed over here, and then x to the 4th. Now, if you knew about the binomial theorem and Pascal's triangle, you could have also just evaluated it using Pascal's triangle. So 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, and this would be the row that you needed. But I haven't covered Pascal's triangle yet. I feel like that belongs more in number theory, which will be a topic I cover after this. So that's that. Now multiplying that, or just first putting it in this expression, x cubed plus 6x squared minus 4x plus 1 over 1 plus x squared dx. So now that we have that, we can just multiply it out. Integral from 0 to 1, x to the 8th minus 4x to the 7th plus 6x to the 4th minus 4x to the 5th plus x to the 4th. And all of this over 1 plus x squared and multiplied by dx. So there's that. But what do we do now? We've already exhausted all our options and there's not really any smart substitutions. So why not we just evaluate it? Why not we just divide this polynomial? We can do all of this huge polynomial divided by 1 plus x squared and maybe we'll get something good. So let's divide some polynomials. So first, let's set up our equation. We have 1 plus x squared, and then over here, sorry, let me draw a better line. That was a really bad line. Let me set it up and show you. All right, over here, we have this entire polynomial, and we're essentially just going to perform long division on this polynomial. Now, if you're not sure what this is, I recommend checking out my video in the algebra series that covers division, or you can also look at other videos online that cover this. And since we are in a calculus series, I assume you know all these skills in algebra, but if you don't, that's perfectly okay. You can just go and review and come back to this. So let's start the process. X to the 8th divided by x squared is x to the 6th. So then you have x to the 8th plus x to the 6th, and then you have to flip the signs as we do in long division. So we do this minus, and we go again. So over here is this x to the 6th is not there, but it does get transferred over here, and the negative 4x to the 7th does get transferred down. So negative 4x to the 7th plus 5x to the 6th. And let's continue solving this problem. 4x to the 7 plus negative 4x to the 7 becomes negative 4x to the 5th. So negative 4x to the 7th minus, now we'll bring down this extra term because we need it, but we'll remember not to bring down any more. So minus 0 minus 4x to the 5th, and then we just flip the signs. This goes away, this goes away, this goes away, so we get 5x to the 6th. But you see over here, this cancels out perfectly. So we run this over here, and there you have it. So since that also worked, we just left with 5x to the 6th. Now we'll add in x to the 4th, and I said earlier I wouldn't, but these canceled out, and we do need another term to divide by. So this becomes plus 5x to the 4th, so 5x to the 6th, and then plus then 5x to the 4th over here, and then we of course subtract it. So we flip the signs on this, minus minus, this gets canceled out, and we are left with negative 4x to the 4th, and there's really nothing else to pull down. So we continue. What we have here is negative 4x to the 4th, so we get negative 4x squared. Then we get negative 4x to the 4th minus 4x squared. So after we flip signs, this becomes the same thing, 4x squared. So what we have is this becomes plus 4, 4x squared plus 4. But then, of course, you have to flip the signs. This cancels out, and we are left with minus 4 as our remainder. So then by the remainder theorem, what we can just do is we can just say minus 4 over x squared plus 1. And that's really about it. And we have just found what we needed to find for our long division. So now that our long division is done, we can go back to actually solving the integral and not just evaluating algebra. So going back to the integral, we can just put the polynomial stuff in one term. So the integral from 0 to 1 of x to the 6th minus 4x to the 5 plus 5x to the 4th minus 4x squared plus 4 dx, and then minus integral from 0 to 1 of 4 times the integral of 1 plus x squared over 1 dx. Now, if anyone remembers the inverse trig integrals, this one becomes arctan of x from 0 to 1. So over here, that's arctan of x, and we just integrate this like a regular polynomial. So what we get is x to the 7 by 7 minus 2x to the 6th by 3, and then plus x to the 5th minus 4 by 3x cubed plus 4x from 0 to 1. And then after that, what happens is we have just minus 4 times tan inverse of x from 0 to 1. And let's start again over here, creating boundaries. This is not the easiest integral, but it is still very achievable. We get, by substituting 1, 0 makes everything 0, so we'll just substitute 1 for the first term. We have 1 by 7 minus, then we have 2 by 3 plus 1 minus 4 by 3 plus 4. Now this becomes minus 2, and then minus 2 plus 1 is minus 1, plus 4 is 3, and 3 plus 1 by 7 is equal to 22 divided by 7. And in a similar way, tan inverse of 1 minus tan inverse of 0 becomes then pi over 4. And the reason is tan inverse of 0, basically tan of what is 0. So tan of, let's say, x is equal to 0. That means since tan is sine by cosine, you can have sine of x equals 0, and that happens at 0. So that's that part. And since tan of x would need to be equal to 1 in this case, and that comes at pi by 4. So we get pi by 4. But we forgot to multiply by 4. So this equals pi. So now we know what the two parts of our integral are. We can go and say 22 over 7 minus pi is the answer to our integral. And since this is a positive number, 22 by 7 minus pi is greater than 0. That means 22 by 7 is greater than pi. And that is our second thing proven. So what have we done? We have evaluated an integral that first looked sort of daunting with this big polynomial, but just dividing it actually gave us a relatively easy integral to evaluate. And after that, we simply did some basic evaluation and found the answer to this integral, and with some of the steps I outlined earlier, proved that 22 by 7 is greater than pi. Now, you can go and say to all your friends that I solved a Putnam problem, or that you solved a Putnam problem. And the reason I'm saying I is, of course, I did this, but also when you solve this, and you can show your friends all of this to say, I did it, I actually solved a Putnam problem. And besides just the flex, it's a really, really interesting competition. Be sure to check out some other more advanced YouTubers' videos on anything from the Putnam competition. It really is extremely, extremely interesting. And besides that, if you enjoyed this video, please make sure to like, subscribe, and hit that notification button for more awesome videos just like this. And if you really do enjoy, you can also leave a comment down below, as that really helps a lot. Any support you do for this channel helps so much to me, and I really hope you continue to do it in the future. But only if you enjoyed the videos and really found them educational or helpful, as I want you to gain something out of these videos also. So once again, thank you so much for watching my videos. You are the best part of what I do. See you in the next one, and bye-bye.